Alright, so I didn't really record a video on Friday, so I'm making it up by telling you about what I learned at PlaySpace today. Okay, I couldn't figure out a good way to like record both my computer audio and also show you the screen, so I'm gonna have this like really jank screen sharing setup. Okay, so what we wanted to find out today is figure out specifically why certain sounds sound good and why different instruments, even though they are playing the same note, can sound different. So we learned about this concept of overtones, which is pretty cool. Has a lot of actually really fun relations that we'll look at later. So overtone, as this says, is a resonant frequency about the fundamental frequency of a sound, right? So when we say like, oh, you're playing an A note, the standard concert tuning for an A note is A equals 440 hertz. So any overtone is basically this fundamental frequency F, which in our case, let's say is 440, multiplied by some natural number or some positive, like real numbers, positive integer, n is n positive. So for example, the second overtone is a whole number multiple, so times 2 of the base frequency, third overtone, fourth overtone, etc. It's pretty funny because it looks like an harmonic series, and it turns out that the harmonic series Wikipedia page also redirects to the overtone page, which is kind of funny. So you have like harmonics in music and harmonics in math, and it's the same shit, which is kind of fun. What else did we learn about? So we learned about timbre, which I think is really cool to kind of see the actual definition of the word. I think I've always kind of heard of it in terms of like, oh, there's like each instrument has like a characteristic sound to it. But it turns out there's like the natural music theory definition of timbre is that you can have two instruments that are kind of tuned to the exact same note. Like for example, A equals 440 hertz, but sound kind of different. And why is that? So even though they play the actual same note, it turns out that the timbre is actually the frequency distribution, the amplitude distribution of all of the overtones. So in this example, we have the fundamental frequency, first overtone, second overtone, third overtone, fourth overtone, etc., right? What is effectively happening is that certain instruments have, the relative amplitude of, their third overtone is different. So maybe this distribution of frequencies is slightly different for like a piano or a cello or the human voice. And that's kind of what gives each sound its unique like profile effectively. And our hypothesis was kind of like, okay, if we can kind of replicate the sound profile of different instruments, we can actually make sounds that sound like instruments in like kind of like it's like pure form, I guess. So the fun thing that we did is we kind of took this sound of a cello and we did a Fourier transform on it to kind of move the sound into the frequency domain. So this is a cello playing the A note of 440 hertz, tuned to 440 hertz. And you'll see the main like fundamental frequency is at 440 hertz roughly right here. There's actually some pretty funny patterns here because there's undertones, which is like a half frequency and even less. Oh wow, there's like a wave feature on Figma, cool. Yeah, and then all the whole number multiples of 220 appear within this, which is kind of fun to look at. And then this top part is what we call the sound envelope of the timbre. So if we draw that here, right, and we map this to like the relative frequencies, so let's say like this lowest frequency that we care about here is roughly like 10k hertz. We map this to like a relative volume of 0, and this highest frequency is relative volume of 1. We kind of can draw this like green envelope line that tells us that this is like, okay, the rough sound profile of a cello. And then at each overtone, we kind of sample the green line to get the relative amplitude of that overtone. It looks like increasingly cramped because the frequency is logarithmic scale, so it just kind of looks like that. Yeah, I was like drawing this diagram, and Matt was like, "Dude, what the fuck are you doing? You're actually this guy." And then he's like, "Yeah, it looks like you're just like trading stocks right now, and maybe yeah, my stock trading strategy should just be me looking at the Fourier transform of a cello. That is maybe what we learned today." So yeah, we effectively sampled this and then figured out that the web browser has an API to play music for you. So, if we head back over to Replit, we have code. We have this specific code to play a sine wave at a specific sampling rate, frequency, and volume using this like oscillator node thing, which, I had no idea existed up until today. But of course, Aslan was like intimately familiar with this API. So we just like asked him a bunch. But I just like kind of manually transcribed this in terms of variables. So I just like eyeballed it and was like, here are the rough frequencies. And then we have this play function that just kind of loops through this entire array and then applies the volume by playing the sine wave. And if we look at the original, so where I got this distribution from was taking like this tuning video, cutting 1 second of the A note and then doing the Fourier transform on it. So this is what it sounds like. Which is a very distinct sound profile. And then if we play the, our computer generated one, it's like, it's rough, but it's there. And the reason why it doesn't sound like exactly there is because if we look at the frequency distribution for the cello, you have a bunch of like frequencies that are like obviously not between or like not exactly at the overtone frequencies, and I think that gives it the fuller sound, whereas we're only sampling at the peaks here, so we get like a much, it's the same sound but it's not as full, if that makes sense. Yeah, so that was kind of our investigation today about like, here is what an overtone is and how to get characteristic sounds. I think next week we're going to focus on like, okay, like why is, like for example, the flute have a different envelope, and like what can we recreate a flute sound, and also comparing it to different like parts of the scale. So like playing a B flat, for example, it looks a lot less regular, right? And part of the reason is like, maybe it's because this is like part of the reason why like flats and parts of the minor scale sound more sad is because, the spacing isn't as regular, so it's more dissonant to our hearing, and therefore dissonance makes us sad. I don't know, maybe. Oh, one last thing that I want to mention is this tri-stimulus representation, because of course, like writing out this really, like trying to figure out the coefficient for each of these peaks is like super laborious, right? So some person was like, yo, what if we just stole like tri-stimulus like theory from color, which is like, you can define a color using like 3 primary things, right? So some music guy was like, yo, can we do that for harmonics? And came up with these 3 variables, T1, T2, and T3. So T1 is like the relative weight of the first harmonic with respect to all of the harmonics. And T2 is the relative weight of the second, third, and fourth harmonic relative to the rest of the harmonics. And T3 is fifth harmonic onwards relative. And it turns out that you can get like pretty much the sound profile of like any instrument pretty reliably just from like these 3 numbers, which is pretty cool. Yeah, so lots of fun intersectional stuff today. Yeah, very fun.